Orbit types, and yesterday we looked at the elliptical orbit, right? Can you guys quickly draw a circular orbit with me?
Yes, sir.
And name some of these. Draw it on a separate sheet of paper. Okay? This will be your quiz. It's simple, right? You remember I think this will be a
You say ellipse or circle?
circular orbit. Okay? Just recall what we did for the elliptical orbit and think about what are those parameters for a circular orbit. Okay? It will be a refresher for elliptical orbits, plus you'll learn something about circular orbit. Okay? So whenever I say circular orbit, what should immediately come to your mind? What is the first thing which comes to your mind? Anybody? E equal to 0, yes. Small e is equal to 0, and what else comes to your mind? Epsilon is less than 0. Okay? So this means the energy is negative energy. Okay? So you have a circle . We talked about 2 points in the ellipse. Which were those 2 points?
The apoapsis and periapsis.
Right, so maybe I should have been more specific. Where is the central body in an ellipse?
At the occupied.
Right. You're going to lose 5 points every time you say the central body is at the center of your exam. Central body is always at focus.
The focus.
Foci is 2. It cannot be at 2 places. Focus is 1. So occupied focus is correct. What happens is, I'll give Anthony an exception in that the focus, occupied focus, and the center are at the same point for a circle. Make sense? Right? Where is the periapsis here?
If it's a circle, then it should be even all around.
Yes, that's a very good point. So you can take periapsis anywhere, but once you fix it, keep to that position. But just for convenience, what we are going to do is we are going to assume this as the periapsis. What is the difference between a periapsis and a perigee?
Well, one of them is like the orbit, and perigee is like if it was on land, it was going to crash back down. No.
Anybody? I'll give you one more example. What is the difference between periapsis and perihelion?
Perihelion?
What does perigee mean? G.
Slowness. Relative.
Periapsis, perigee is
That's not happening, you know.
periapsis with central body as Earth. G. Geo. Okay. Helion, perihelion. Make sense? Helios. Yes. Is periapsis with central body as
So what would the moon be? Perry, Luna.
you're going to find out and tell me what it is.
So each
Every planet has. So periapsis is a general term for any central body and any orbiting body. Okay, these are specific. If you're going to, anytime you hear some news from NASA, they are not going to use periapsis. They always talk to you in terms of perigee because they are always talking in terms of Earth orbitals. Okay, but when we go to Mars, when the Mars becomes, do we put a lot of satellites around Mars or Moon?
Not as many as Earth.
Not as many as, at least not utility wise. Mars and Moon, what do? We do exploration. Okay, we do science. Earth, there is utility in terms of. Can you name the utility of satellites in terms of Earth?
Yes.
GPS, communications,
Missile defense. That'd be like
weather.
Ionized laser.
It's not application. What would you do with ionized laser? But think about utilities. Utilities to common man. Alright? So you talk about communications, GPS, weather satellites, TV satellites, right? All those are utilities. So we know where the focus is, occupied focus, unoccupied focus and center are at the same point. Does this make sense?
Yes.
We are going to just take this point as the apoapsis. What do you know about RA equal to? RP is equal to R, right? Is equal to A is equal to. Does this make sense? This is RA, right? This is RP. All this is R. What is A? You can say this is A, right? And you typically know that this is B. So for a circle, this is RA, this is RP, this is RA. Okay? All these are the same. You understand?
right.
Now, depending on where the satellite is, I think we forgot to introduce something very important, the elliptical orbit. This is R, right?
Yep.
What is this?
Theta.
Theta. We did? Right. So, this theta, you have to understand, pay attention here guys. Look at me. Remember this formula? Orbit equation. What is the orbit equation? H square over mu 1 plus
E cosine
E
theta.
cosine theta. So here, what I told you was, if you're given an orbit, right? This is constant, h is constant, mu is constant, h is a function of the orbit, okay? The size of the orbit. Mu is a function of the central body. E is a function of the shape of the orbit. This theta is varying. You understand? When it is here, the theta is, when the satellite is at the periapsis,
0.
the theta is 0. Okay?
Which is, you said, I missed, you said something, so cosine theta is
Varying.
it's what?
Varying. Theta is varying. Okay? R is a function of theta. Does that make sense? So your R is changing. If you write this, strictly speaking, you would write this as R of P is equal to H square mu 1 plus E cosine You got it? Okay? Keep this in mind. Always. Alright? So this is, if this is R1, this would be theta 1. What is theta P?
For circle should not be 0.
Is it not just for circle? It's for everything, it's 0. What is theta P? Theta P is essentially when the satellite is here, okay, and this angle, the angle is taken from that periapsis. Angle is measured from the periapsis direction. Okay, this theta P is always 0. Alright? What is RP in that case? H square mu 1 plus E. You got it? What is RA? One, because theta is 180. Okay? This is the case for all orbits. Alright? What do we know for our circle? This E is what is this E for our circle? 0. Right? So this is, we have derived this. So our circle is equal to RA is equal to RP is equal to A is equal to B is equal to okay. Does this make sense? Any questions on this one?
E doesn't stand for anything. E doesn't. It's not a.
Eccentricity.
E right there. E is right there.
E here is eccentricity. This is
Specific.
epsilon. What is it?
So specific.
Total specific mechanical pressure. What quantity is this? Huh? What? Huh?
You're talking about like.
What quantity is this? Now, if you were to distinguish between what quantity is this and what quantity is this, this is a geometrical or a math quantity. Okay. This is physics. This is a physical quantity. Total mechanical energy is physics. You get it? You understand?
What do you mean by that?
Eccentricity, does it have any physical meaning? Can you see eccentricity? Can you feel eccentricity?
You can't measure it though.
You can measure it. So something which can be measured is
Real.
it's a mathematical quantity.
Okay. I see.
Can you really measure eccentricity or can you compute eccentricity? You can compute eccentricity, right?
So you measure it.
How are you going to measure eccentricity?
Because
On circuit or
yeah, we measure it.
Eccentricity is a ratio, right?
something.
All ratios are mathematical.
Like, is it
Reynolds number, is it a mathematical quantity or a physical quantity? It doesn't have, it has its physical interpretation, but it is a strictly mathematical quantity. You get it?
What's the distance of RA? Is it just R1 or
What is the distance? What do you mean?
you said RA equals RP equals Which one's R?
R is just RP is specifically this. When the satellite is here, this becomes RP. But all other is R. What happens is, what you have to understand here is R is changing. Okay. At P, this theta becomes 0. That becomes RP. Okay. And for a circle, this becomes, E becomes 0. Right? This becomes R circle.
So what about RA?
Theta becomes 180.
Okay.
That becomes RA. You understand?
No, what I was asking was, how is RA equals RP equals to R? R is always changing. RA and RP's.
In circle, so this is, you have to understand the R, what is changing here?
Location.
The
Talk
position of
like
the
a,
satellite.
huh?
Position,
Talk like a aerospace engineer. What is changing here in terms of R?
It is specific.
The magnitude and direction are changing, right?
Right.
This, what is this?
That's
That's magnitude. Does that make sense? I don't have a vector in there, right?
right.
Invariably, RP is in the P direction. What is RP? Does that make sense? You could have written this. This RP is R. This is a case for circle. This R is not changing for a circle. You understand? But this, sorry, the direction. This is changing. RP is not changing, obviously. Okay, RP is always in the direction of the periapsis. But R is changing. Even for the direction of R is changing. The magnitude is the same. Does that make sense? Because you see, R has to give you the relative position of the orbiting body with respect to the central body. If it is, the magnitude will be the same if it is going in a circular orbit. But the direction is changing. How is that direction indicated? Tell me, how is that direction indicated? Huh? Theta. Theta is the direction. You got
When we use RT.
it?
When would you use RT?
All this is RT. So RT is, this is just a function of time.
Yeah.
It's always like this. If I write it like this, you have to understand what is constant here, what is variable. And we did that when we derived the R relation. Okay.
Dr. Sunny.
Yeah.
So I go back a little bit. Next to what you written epsilon there, what do you have for next that says total specific?
Total specific mechanical energy. Okay. All right, so will you be able to draw these in an exam and label all the different parameters?
So we have to do this and an ellipse, or it'll be either this or ellipse?
Yeah, both you have to do both. You have to actually do 2 more.
With the equations?
Huh?
With the equations?
No, this will be one question. You'll definitely get one question on drawing an orbit and labeling the parameters. Orbital
Don't say
parameters.
that you want equations too.
Those will be separate.
Okay.
So it's
That
not
would be
just.
one question.
Huh?
The drawing will be one question, and then the equation will be the rest.
You'll have derivations, you'll have formulas, you'll have problems. So, for example, if I ask you, prove or show RA is equal to h square over mu divided by 1 minus e. Can you prove this? Starting from orbit equation. Can you do this?
Yeah, that's just.
That's just part of it, right?
Could you just,
RA.
Okay.
you just walk me through it?
Huh?
You just walk me through it?
Can you do this?
Man, look back on the notes.
Prove Rp is equal to a square over mu over 1 plus e starting from orbit equation. That's all.
Oh, so simple.
It's a 1-line derivation.
Why don't you say, do you have to have a picture of it? Or
I just show it.
Huh?
I want to show it. He wants to look at it right now.
Do you understand this question? Okay. Where will you start for this question?
For certain, orbit equation.
Start with orbit, you draw an orbit. As you draw an orbit, you say.
You're not reading what is being given to you. Where do you start?
Orbit equation.
So the orbit
Your orbit equation, I've written the orbit equation, just read that.
h squared over mu over 1 plus e cosine theta.
Yeah, that is the orbit equation. How do you get from this to this?
Say theta equals 180.
Is that so difficult?
Yeah.
That's what I show.
That's it.
No, you don't need to illustrate.
Hmm?
You don't need to illustrate.
Illustrate in the exam.
Okay.
Okay?
Illustrate.
So you say that RA, you say at RA, theta equals 180, right?
Yeah.
You
If I ask you to draw an orbit and prove these two, starting from orbit equation,
I just want to make sure you know I feel like you got
you need to show me that you know what you're doing. Otherwise,
I realize it's too simple. So
all right. So let's look at the parabolic orbit. What do you know about the parabolic orbit?
Zero.
All right.
And then epsilon is 0, 0.
Okay. So what you have to realize here is, guys, pay attention here. Okay. You're talking too much. Okay. This is the
Our focus.
what focus is this?
This is occupied.
Occupied sun. Okay. What do you know about this point is very active, right? what is this direction? And this is true for all orbits. That's all. That's simple. Okay. It's a periapsis direction. What is the periapsis direction? The line joining focus and periapsis and moving on. That's the periapsis direction. Okay. What do you know about R for a parabolic orbit?
We go to, infinity.
Does this make sense?
R all orbits.
How did I get this?
You started with the over.
E is 1.
And I was
Okay. What do you know about RP? It is still okay.
How does the
Oh.
how does the orbit work?
So what you do is let's say that's a good question. So I'm going to answer this once. Please pay attention here. How does an orbit work? Okay. So this is your central body. All right. What you do is I'll draw a little bit bigger. So you have seen this several times. This is the central body, okay? Let's say Earth, right? What you're going to do is, this is the surface, right? You're going to launch your rocket like this and throw the satellite in here. When you see, if you see the rocket launches, they go like this, they do that, right? They go like this and they do that. And when they're doing that, they deploy the satellite. When you throw this, the position, depending on position and velocity, this will start orbiting. You have given a certain velocity to this. The velocity is going to push it in a tangential this thing. So it's going to, it's like if you tie a stone to a thread and do that, it is trying to get away, right? That stone is trying to get away. But what is holding it back? The string. Here what is holding it back? The gravitational force is not going to let it go away, but the velocity with its, that velocity, there is a change in momentum, right? That thrust is going to keep it going. So this is the orbit. You got it?
So with the parabolic orbit?
Yes, so parabolic orbit also will do that. So if you're doing a parabolic orbit, typically parabolic orbit, what happens is, you get into this orbit, okay? Let's say you're trying to get into Moon's orbit, right? You do this, you do phi or something here, you get into an elliptical orbit. You increase this, right? When you're here, what you do is you decrease the velocity, so you get into this. Okay? And then what you do is, let's say you want to escape that. You try to swing here. If you want to get into the orbit of Moon, you will decrease the velocity here. If you want to just swing off, or what is it called? Slingshot or flyby. If you want to fly by something, right? You're going to launch it with sufficient velocity. When it comes here, it's going to, this is, see, the force is like this, right? I told you the the merry-go-round.
Right.
When it is rotating, there is centrifugal force here, right?
Yeah.
So when you are trying to, you are running and you are trying to hold on to it, right? What it will do is, it will throw you. You can imagine, right? That, right? So this is going to throw you. When you're thrown, after you're thrown away, if you have enough energy, you'll get into a hyperbolic orbit. You'll keep going past this. But if this catches you completely, you'll get into a closed orbit. If it is between catching you and throwing you far enough, you'll get into a parabolic orbit. Does that make sense? You never intentionally want to get into a parabolic orbit.
Okay. So,
Huh? But it's a reality.
Would just turn back.
It'll go to this point, okay? Alright? And what's happening is, this is trying to pull it, but it doesn't have enough this thing. This is trying to go away, it doesn't have enough this thing. So it's like, the path this is following is this. This is going around Earth, right? So this is coming like this. It's always chasing. It will never reach there, but plus it's not going to get out of that orbit.
so
So if in a hyperbolic orbit, what happens is this has gone. Only this is chasing now.
with a parabolic orbit, after it escapes and it wants to.
It doesn't escape.
So it's just in between.
It's in between.
So that's in the state.
Do you know what escape velocity is?
No.
I mean,
Yeah, escape velocity is essentially, I'll talk about that. Okay. So this is where we are exactly at that point. Let's do this. You're okay with this? I took the orbit equation. Orbit equation is very critical. Substituted E equal to 1. Right? This, what I did here was, for RP, what is this? 1. Cosine theta, right? Because 0, right? Theta is 0, you get 2. What is RA? If this is infinity, makes sense?
Yes.
can you explain it?
There isn't anything here.
So that's also so
The apoapsis is at infinity. You understand? Because it's a open orbit.
it just goes on forever.
So if you don't do well in your exam and you become an astronaut, you'll be. Torres,
Yeah, I had a question.
you make sure you understand this
I
and put enough thrust so that you don't get stuck. Nobody's going to come and recover. Alright, what is your question?
So if we plug in E equals 1, how come we didn't do that for circle orbit?
Because E is equal to 0 for circular orbit.
I know, so I don't just plug it in though.
Huh?
How come we didn't plug it in if we plug it
We
in?
did.
E equals 0?
Yeah, we did.
You did.
I showed you. Alright.
No, I'm saying, but he's saying he didn't plug in 0 for E, he plugged in theta. You plug in theta. Because if he plugged in E equals 0, then it would just be 1.
Right. So we did this. We did R square, R circle. You remember we did this last class. Because E is equal to 0.
Right, I'm saying, why don't you do the same thing? You just trying to write it differently? Or?
We did this. E equal to 0.
Yeah, I'm saying, why would we do something different right here?
That is for all orbits.
Okay. I see what you're saying.
Yeah, it's good.
I put this thing and said all orbits RP. I wanted to derive a relationship for RP and RA. Okay.
That makes sense.
So you have, now I'll answer your question, Joshua. What do you know about energy equation? E is equal to V square over 2, right? Minus mu over r, right? What is epsilon? Epsilon is equal to 0, right? For
Pure ball.
Right.
right?
Right.
So you have v square over 2 is equal to
Zero.
mu over r.
Mu over r.
What is this? So I can write this v is equal to root of 2 into root of mu over r. You with me?
Yes, sir.
Everybody? What does this mean?
Escape cross.
This is the v escape. Okay? And this is what is this? We derived this relationship. Just look back into notes. You are in a circular orbit. You increase the speed by root 2, 1.14. What's going to happen?
You escape.
You escape. If you increase it exactly by 1.14 or root 2, what's going to happen?
You say if you increase it by.
You're in a circular orbit. So v circular is that, right? So the velocity in a circular orbit is same always, right? You increase the speed, you fire your thrusters by root 2, right? You get into a
Escape velocity.
parabolic orbit.
Slash parabolic.
You increase it more than root 2, you get into a. Does that make sense?
It does.
Wait, so as you increase the velocity, you move into an escape route,
Right. So when you are orbiting, if you increase, you go into a bigger orbit. The limit is if you don't want to escape or you don't want to go outside the gravitational pull of something. What is the this thing? Ceiling?
Appreciate the root.
Root 2.
That was the ceiling. Right?
So if you are in any circular orbit, if you increase it by root 2 times, you're going to get to escape. Exactly that. If you increase it slightly more, you're going to go into a hyperbolic orbit.
So, I don't know if you said this, so the parabolic orbit has similar characteristics to the circle.
No. So if you want to escape, you typically don't escape from ground. Then you would need a lot of fuel. You understand? What you do is anytime you want to escape, when do we escape? When have we escaped?
You escape while you're over.
No, what is a practical example when we had to escape? When we have escaped? Apollo mission, right? We had to escape. When else had to be escape? When we launched the Mars orbiter or Curiosity, we had to escape, right? We couldn't carry all that fuel and then directly run out. Understand? We had to get into circular orbit or an orbit first, throw off all the load, and then increase the velocity from there to escape.
Is that the fastest one?
So we get into a circular orbit first, and then whatever depending on it doesn't matter what circular orbit it is. We get into a convenient circular orbit, and then we increase the speed by 1.41 times. What's going to happen? We're going to escape.
So this going to a circle orbit to escape is one of the easiest and most fuel efficient.
Right. So it's the way to do it. You don't want to just the large amount of fuel is really needed for. Why do you need large amount of fuels for Have you seen how light the orbiters are?
They're small. Need a lot of fuel to escape Earth's gravity.
Is it really Earth's gravity?
Well, I mean, the atmosphere.
Atmosphere.
I mean,
The rockets use that much fuel because it has to escape Earth's the atmospheric resistance.
And when you, and what did you say happens again to increase it? As?
It'll go into a hyperbolic. It'll escape and keep going.
It'll escape and keep going.
Keep going to somewhere else.
that's like, oh,
No, that's different. We'll talk about-
Is a circular orbit the fastest orbit you can be in? Like in terms of your velocity?
What do you know? There is no fastest orbit in terms of shape.
Is it on the
Depends on how close or how far you are from. Okay. So, for example, if this is your circular orbit, okay, and this would be your elliptical orbit. At this point, both the orbits have the same speed. It's a function of distance from the. Right?
So you're you ever be outside of you be like completely outside of orbit, say you're between two planets, you're going directly.
Yeah. So the L2 point where the James Webb Space Telescope is going, it's the point where the sun's gravitational pull and the Earth's gravitational pull are exactly the same. And that if you go there, there is almost zero gravitational pull. And that's
what is that called? What is that point
the
called?
L2 point, L1, L2,
Like the brain?
Lagrange point. Yeah.
Yeah,
Well, typically something hyperbolic when they're traveling.
So hyperbolic orbit is more of a flyby, or if you want to go to another planet far off, and if there is something in between, you use the gravitational pull.